everyone, welcome back to the tutorials on the mechanical vibrations. Today we are going to wrap up the topic of free vibration of a single degree of freedom systems under viscous damping. So let's begin. So as usual, let's have a quick review on what we had before and what is the free vibration of a single degree of freedom system under viscous damping. So as you may remember from before, we have a system like this, like a mass. Well, ideally we have a spring connection with the spring constant of K, and then a damper, which we can show it like this, and has a damping constant of C, and X is our degree of freedom. And because of an initial condition, whether it's a velocity or a displacement, we have vibration in the system, and the system stops because of the existing of damping, right? So the equation of motion is mx double dot plus kx plus cx dot equal to 0, or you can write down cx dot plus kx equal to 0. And as you see, it's a second order differential equation, so we have x at 0 or x naught and x dot at 0 or x dot naught. So these are the initial conditions that we need to solve the problem. In many cases, one of them is 0. However, we need at least one to be non-zero to have a vibration in the system, and a non-trivial response for the system. And then we discussed some of the parameters we have in the system, such as the undamped frequency or natural frequency equal to square root of k over m. We also have the damped frequency of vibration, which is equal to 1 minus zeta squared omega n, and zeta is the damping ratio over C critical, and C critical is basically a constant based on the parameters of the system, which is, for example, equal to 2m omega n. And then we also discussed that the response of the system, depending on the zeta value, whether it is less than 1, whether it is equal to 1, or greater than 1, would be different. We had three cases: the underdamped system, the critically damped system, and the overdamped system. And we showed that the response of the system could be either a sort of harmonic for a undamped system, it could be a sort of quick stop for a critical damped system. So let me use another color just to indicate this is for a critical damping, and it could be something like this and then stops, or it's not harmonic. Let me just show it again. So I'm gonna use another color, and it could be something like this and slowly stopping for a overdamped system. So as you can see, we have different cases, and today we are going to discuss a little bit on the critically damped system, which is very important in the design problems when you want to stop the system as soon as possible. And then we have another example for a underdamped system. So basically these two cases are more important to investigate in vibration systems. So let's do that. Okay, so let's start the first problem, which is on a critically damped system, and see how we can dig into this problem. So let's just quickly go over the problem and see what we have. So in this system, or in this problem, we are looking to find the time at which a critically damped system has a maximum value, the amplitude of the vibration. And also we want to find the expression for that maximum response. So in fact, we are looking for a time, and we call it Tm, which gives us Xm, and Xm is the maximum amplitude for a critically damped system. So as you may remember, a critically damped system means that zeta is equal to 1, and the behavior of the system, depending on the initial condition, could be different. So assume that we have a positive initial condition, for example, a positive displacement x0 greater than 0, right? So the system starts to vibrate somewhere here. So this is actually T, or basically let me draw it bigger and elaborate the behavior of the response more clearly. So I'm gonna draw a better axis. So we have T, and this is basically X, T, the vibration of the system. So if we suppose that we have a positive initial displacement, it means that the system starts to vibrate at a point x naught, right? And the reason that we selected it positive is because we don't want to, we want a maximum value for the amplitude, so we are not going to start from a negative value because the system goes to 0 or something like that, right? So that's why we select x naught as a positive value. And now let's look at the initial velocity when we have x dot naught. So as you know, the velocity or x dot is the slope of x, right? So if we have x naught equal to 0, let's see what happens. It means that the slope is 0, so the system behaves something like this, right? So let me, to make it more clear, just erase these two lines and then assign this curve to the case that we have the slope equal to 0. So this is for the case that we have x dot naught equal to 0. Now let's imagine the case that the x naught is, or x dot naught is negative, so the slope is negative. The system would be let's say something like this, right? So the slope is 0, the slope is negative, which means that this case is for the case that x dot naught is less than 0. So to not get confused, I'm gonna just use another arrow for the first case, which belongs to the slope equal to 0. And lastly, the case that the slope is positive, or we have a positive initial velocity. What happens is the system acts like this, right? So the slope is positive, and this gives us the case that x dot naught is greater than 0. So based on the problem, in order to have a max value for the displacement, we are dealing with this case. So as you see, there is a point that gives us a maximum of xn, and we are looking for the t, which gives us the maximum amplitude. So this is the case that we need to investigate. So it means that we need a positive slope and we need a concavity downward, right? But for all these cases, no matter what the initial condition is, we know that the response of a critically damped system, the expression is explicit, and we know that xt, no matter what the initial condition is, for a critically damped system is equal to x naught plus x dot naught plus omega n x naught t times e minus omega n t. So this is the expression that we already know from the basically the textbook, and we don't have to be worried about that. So let me just write it in a clear way. So I'm gonna use again the expression times e minus omega n t. So here there is no like meaningful natural frequency, but omega n is basically the frequency of the undamped system. So this is the response of a critically damped system, right? And no matter what the initial condition is, then the initial condition identifies which of these curves we deal with. So now we know for this problem, to get a max value or a time that gives us a maximum value of amplitude or displacement, we need to ensure that x naught is positive and x dot naught is also positive. So these are our conditions for this problem. So let's continue and see how we can find the time that we get the maximum and how or what is the maximum value for the amplitude at that time. Okay, so we know that based on the math, if we have an equation and we want to find either a minimum or a maximum, we need to find the first derivative and set it equal to 0 to find the independent variable, right? So for this case, we already know the expression for xt, which is equal to, as I showed in my previous slide, x naught plus x dot naught plus omega n x naught times t e minus omega n t, right? So we just need to find dx versus dt to find the extremum, or either maximum or minimum. So if we find the derivative using the chain rule, I hope you can do that from your math knowledge, is equal to e minus omega n t times minus x dot naught plus omega n x dot x naught, sorry, omega n t plus x dot naught, right? So this is just the derivative using the chain rule. And after we use that and finding the derivative, we have to set it equal to 0 to find the t that whether gives us the maximum or minimum. And as you may remember, we are looking for the maximum. So we set this equation equal to 0. And as you look at this equation, this is an exponential term, which is also, there is a negative power, which means that it becomes 0 only at t equal to infinity. So in order to make this equation equal to 0, we have to set this part equal to 0. So we don't need to be worried about this part. So we set this part equal to 0 to find t. And as you see, t is here, so we can simply find it out through this brackets, and therefore the t, which gives us the maximum, or we want the maximum, is equal to x dot naught divided by omega n x dot naught plus omega n x naught, right? So this is the t that we expect to give us the maximum amplitude, right? But we need to ensure that for this case, or for this response, the concavity is downward to ensure that basically we have this behavior, right? And there is a maximum, so the concavity is downward. And as you remember from your math courses, to ensure that, we need to find the second derivative, right? So we need to find d to x over dt squared and ensure that it is a basically either positive or negative. And if we want to have it downward, we need to ensure that this is at this tm, it is downward, right? So let's check that. We need to check, right? And ensure that we get a max at tm, right? Okay. So if we find the second derivative, and as you can do that through your basically your math knowledge and finding the derivative of an equation, d2x over dt2 is equal to, I just write the final expression is minus e minus omega n t times 2 omega n x dot naught plus omega n squared x naught minus omega n squared x dot naught plus omega n x naught times t, and that's it, right? So we found the second derivative, and now we need to plug in t equals to tm into the above equation. So let me just use another color. So in this equation, we set t equal to tm. So in fact, we need to plug in tm in above equation. And if we do this and we simplify it, we can find basically this dt x squared dt2 at t equals to tm is equal to minus e minus omega n times, as you may remember, we had the expression for tm in the previous slide, omega n x dot naught plus omega n x naught times omega n x dot naught plus omega n squared x naught, right? So we basically found the second derivative and we plugged in tm into it. So again, let's look at this equation and see what is the sign of this equation, or this expression, to find the concavity direction. So look at this part. This part is always negative because we have an exponential term and there is a negative sign here. And now looking to this part, we know that the condition we initially defined is x dot naught and x naught are both positive. You remember my drawing, right? We have the initial point and initial slope positive. So looking into this equation and knowing that the natural frequency is always positive, so the whole bracket in here is positive. So we have a positive here and we have a negative here, which means that the whole d2x divided by dt2, or the second derivative d2x dt2 at t equal to tm would be a negative value, right? Which means that we have a concavity downward, which ensures that at tm, right, we get a maximum value for x. So our condition and our calculation is correct. So we can use tm to find xm, which is what we're looking for, the maximum displacement for this critically damped condition. So the rest would be very easy because we ensured that tm gives us the maximum displacement. So what we need to do, just plug in tm into the xt expression. So x max is equal to when t is equal to tm, and we just simply plug in into the expression we have, and after we simplify that, we can find this is equal to x naught plus I just need to plug in t into the expression we have for x omega n, x naught times t, which is tm here, x dot naught divided by omega n, x dot naught plus omega n, x naught times e minus omega n, and here is tm, so we just use the tm in there. So if we do this and we simplify it, it would be equal to x naught plus x dot naught divided by omega n times e minus x dot naught plus omega n x dot times omega n, right? So we basically we'll be able to simplify the system by plugging in the tm into the x expression to find the maximum amplitude or maximum displacement for the critically damped case. So at tm we will be able to find x, right? So that's a very detailed analysis on a critically damped system, and I hope you got the idea about these types of systems. Now we can continue to another example, which is about a sort of underdamped system, which is also a very important case for vibrational systems. Okay, so in this example we have a combination of a mass under a sort of translational motion, and also the rotation of a pulley with the moment of inertia of J naught. However, the two masses are sort of like their motion is linearly dependent, which means that we can convert the whole system into an equivalent mass, spring, and damping case, which means that we have a single degree of freedom system. And as you can notice, the natural frequency omega n of the vibration is given as 5 Hz. Other parameters like the mass, the J naught, the radius, the inner radius and outer radius are given. So the problem is saying if the system is disturbed by an initial displacement and the amplitude of free vibration reduced 80% in 10 cycles, what are the values of K and C? So it is a very interesting problem. It's not just regular type of solving and finding the response of the system. In this case, we have some relationships between the amplitude decrement, and we need to find the constant of C and K in this problem. So at the first stage, we need to find the equation of motion and find equivalent mass, spring, and damping parameters. So let's look at this problem and see what's going on. So if we look at x and we give a sort of virtual rotation to the disk calling theta, and knowing that theta is basically the degree of freedom of the pulley, right? Let's see what is the relationship between theta and x. So if we look at this system and we suppose that we have a small amplitude of vibration, or theta is small or x is small, because it's a vibrating system, we can suppose that theta is a small value. Say for example, if it is less than 6 degrees, and then we can suppose that the sine of theta equal to the tan of theta equal to the theta, right? We know that, and we had these assumptions before. So let's look at this. So this is basically the linear motion or the translational motion in this point when we have a small theta, which is in fact x, right? So if this mass goes this amount, like x, and it makes the pulley to rotate for theta, and this amount of displacement is also x. And if we look at these relationships, we see that x is equal to, nearly equal to r to theta, right? We can have these sort of assumptions. So this x is equal to this one, and which is like using the relationship between theta and r, we can use x is equal to r2 theta, and r2 is the, you know, the outer or the larger diameter, right? So just keep this in mind. This is very important, and we need to use that in the future when we want to make only one basically equation of motion, right? Okay, now let's look at this system, the mass system. I want to basically draw it here. So if we have the x displacement in the system, we are going to compress this spring K, and this causes a force against our mass, right, which is equal to Kx. And at the same time, we have this rope or this basically connection, which causes a sort of, you know, force on the system, right? So in fact, we have a force against the motion because of this pulley and the rope on it. So we have this force, we can even call it P. So if it is P this way, it is in the opposite way at the side of pulley. You may remember that from dynamics, right? So we have P, and it's the same amount, supposing that there is no elasticity or nothing in the rope, the P is equal through that, right? This is all you may remember from statics or dynamics, right? So we have P here. Now, if we use the Newton's law, we have basically sigma F is equal to basically, you know, m x double dot, and from that we can find basically P is equal to minus m x double dot minus kx, right? How we can find that? Just like imagine if we use this equation, we have F is equal to minus P minus kx, right? So we can simply set it equal to mx double dot, and then by simplification we get P equal to mx double dot minus kx. So keep this in mind because we are going to use that in the future. Okay, so we are almost done with this part, which is m. Now let's look at the pulley. So I'm going to draw it a little bit larger and see what's going on here. So this is the inner circle, and let's see what are the forces acting on the system, so that then we can use the Newton's formula. So the first force is basically this P that we found the expression before for that, minus mx double dot minus kx. And also there is a damping force, right? If this is the damping, we have a damping force acting on the system, which is equal to basically c times the velocity of the deflection. So the deflection is something here, so this is delta, and knowing that with the same process we used before, delta here is equal to r1 theta, right? Because this is actually the theta for a virtual basically motion, and c delta dot is the force on the damping, and here it is equal to basically CR1 theta dot. That's it, right? So we have the two forces acting on the pulley. So this is minus mx double dot minus kx. So now let's use the Newton's law for the mass, for the pulley basically around point O, which is equal to JO theta double dot. And if we know the forces acting on the system, we can write JO theta double dot, and knowing that JO is basically given in the problem, or we can use the formula for this, it's equal to P times the arm of moment, which is R2. So we have minus mx double dot minus kx times R2, right? And then we have basically the force of damping minus CR1 theta dot times the arm of moment, which is R1, right? Because for this force, this is the R, right? Or we can basically do it step by step and figure out the terms. If we simplify it, and knowing that theta is basically R2 theta is equal to x, and therefore x double dot is equal to R2 theta double dot, we can further simplify this equation to only have one variable, either theta or x, in our differential equation. So we have this derived equation. We just need to plug in these expressions on it and further simplify it, right? So if we do this, we can get basically JO plus MR2 squared. This is from the x term. Basically theta double dot and m is this mass, plus CR1 squared theta dot plus K R2 squared theta equal to 0. So this is the equation of motion after we simplify everything and put everything in the left hand side. So let's use the numbers and the values we have. So we get basically 5, which is J, plus 10, the mass, times R2, which is 25 centimeters, times theta double dot, plus C times 0.1, 10 centimeters squared theta dot, plus K 0.25 squared theta equal to 0. And you remember we were looking for the C and K. So let's do this calculation and further simplify it. We get 5.625 theta double dot plus 0.01 C theta dot plus 0.0625 K theta equal to 0. So let's look at this equation and see what we have. So we basically simplified our system to a one single degree of freedom equation because theta and x were related to each other, and this is basically our equivalent stiffness mass. We can call it MEQ here, and this is CEQ, and this is K equivalent, right? So we will be able to find these terms and simplify our system. It's theta. You can also use JEQ if you want, so don't worry about that. I just use the notation. So the natural frequency of the system is given as 5 Hertz, and you know we have to convert it to radian per second, which is 10 pi radian per second. We just multiply it by 2 pi, and we know that this is equal to K equal over M equal, right? So by that we can simplify K. So let's do that and find K, which is one of the unknown that we need to find for this problem, right? So if we do this, and we have basically 2 pi times 5 Hertz equal to, what was K equal? 0.0625 K divided by the equivalent mass, 5.625. We found them before, or in fact instead of this you can use 10 pi, then we can find k, right? It is pretty simple. Just power the two sides and use cross multiplication. Then you can find k as 8.88 10 to the power of 4 Newton per meter, right? So this is 4 basically. Okay, so we will be able to find k simply from the natural frequency formula and knowing equivalent mass and stiffness. This is the easy part. However, there is a tricky part about finding c. So how can we find c basically for this problem? As you may remember from my previous tutorial, I discussed the logarithmic decrement and how we can relate the decrement of amplitudes based on the parameters and constant of a system when we have a viscous damping and we have an underdamped condition. So for example, if this is the behavior, I told you we can basically find the relationship between each amplitude and at each cycle. And basically, generally speaking, if this is x1 and we have xm, for example, at mth cycle, we can write x1 over xm plus 1, which is the amplitude at the first cycle, and the m plus 1 cycle is equal to e m zeta omega n tau d. So this is the formula we have based on the logarithmic decrement, and this is actually very important to know and how to use that when we have basically even a practical case and we want to basically estimate the behavior of the system. So this is the logarithmic decrement, right? So this is the formula we need to use in this case, right? So we know that at 10th cycle, basically based on the parameters given in the system, the amplitude decays to like for 80%, so that we can ensure that how we can use m, how we can select m, and how we can basically simplify the system. So for this case, we know that m is equal to 10. Basically, the 10th cycle, the information for the 10th cycle is given, and we have a reduction of 80%. This is all given from the problem statement. So what we can do, we just plug in into the formula. So we have x1 to x10 plus 1, which is m. We have a reduction of 80%. So if this is 1, it is 0.2. 0.2 means 20%, right? So this is just a simplification. It is equal to 5, because if we just simplify this fraction, we get it 5. And it is equal to the formula I wrote for m equal to 10, right? Which is equal to e to the power of 10 zeta omega n and tau d. And you will see why I'm doing this. If we take the ln of this equation, basically if we take the ln of each side of this equation, we can further simplify it and get rid of e. So ln of 5 is equal to the ln of e, which means that we cancel out e. It is equal to 10 zeta omega n tau d. Right? So we can even further simplify it. We already know omega n. So omega n was 10 pi, which is equal to 31 point something. You know that. And what is tau d? Tau d is 1 over or 2 pi over omega d, which is equal to 2 pi divided by 1 minus zeta squared omega n. Right? So as you look at this equation, we can even have omega n here. So omega n was 10 pi, so we can plug it in here. So tau d is equal to 0.2 divided by 1 minus zeta squared, right? How can we find it? We just simply use this in here, and then we can have this expression for tau d. So we found ln of 5 equal to 10 zeta omega n tau d, and we know how to figure out tau d and even omega n. So ln of 5 is 1.6094 equal to 10 times zeta times omega n was 10 pi times tau d, we found it as 0.2 over 1 minus zeta squared. So let's look at this equation. The only unknown variable is zeta, so we can simply find zeta out of this equation, right? If we further simplify it, how we can do that? We just need to do some multiplication and powering the two sides. We can find basically zeta as 0.0256, and it has no units, right? So as you can see, the only variable is zeta here. We can find it. So we found zeta. Zeta is equal to C equivalent for this system divided by C critical, which is equal to 0.01 C, the main unknown variable that we are looking for, divided by 2m equal times omega n. So as we look at this, we have everything here. We know m equal omega n, so it is equal to 0.01 C divided by 2 times 5.6, or let me just use cross here, 25 times omega n, which is 10 pi, and this is equal to 0.0256. So the only unknown is C, which can be found simply from above equation, which is equal to 900 something, like 5 or so Newton second per meter. So you can double check my calculation. So as you can see, we could be basically able to find the two unknowns based on the information given using the logarithmic decrement, using the equivalence system. So in the two examples we have today, we basically covered two main cases, and plus the previous tutorial, we almost covered the whole system of a single degree of freedom system under viscous damping when we have a free vibration, right? So I hope you enjoyed today's video, and stay tuned for the next videos.